Hey guys, today we're going to be talking about trigonometry on the unit circle and some conventions with regards to how we plot these things. We're going to talk about angles in standard position, coterminal angles, reference angles, and trig ratios in each quadrant. We're also going to talk about how to determine their signs. And then finally, we're going to talk about special triangles, which are specific ratios that we can use to determine trig functions for certain values of theta, like 30 degrees, 45 degrees, 60 degrees, and 90 degrees. We can do this without a calculator using special triangles. Let's get into it. So first off, trig in the Cartesian coordinate. Angles are plotted on the Cartesian coordinate, starting from the x-axis and moving towards the terminal arm. So the terminal arm and the x-axis are basically the two arms of the angle. The terminal arm is the arm that moves, and theta is formed between it and the x-axis that looks like this. The terminal arm is always centered on the point 0, 0, unless stated otherwise, and it moves counterclockwise. As it completes a full rotation, causing theta to expand like that, it has traveled a total of 360 degrees. Now, coterminal angles are basically just that. A 30-degree angle is coterminal to a 390-degree angle. That is because a coterminal angle, I'm just going to label this as theta, and have the coterminal angle come like that. That's theta 2. A coterminal angle is just the same angle plus 360 degrees. So it's completed one more full rotation than the angle that it is coterminal to. A coterminal angle could also be, like, if we were talking about 30 degrees here, it would also be 750 degrees. So 2 spins, but same angle. It could also be negative. So a coterminal angle to 30 degrees would be negative 330 degrees, which is basically theta going the other way by 330 degrees. Notice the same angle is still formed between the terminal arm and the x-axis for all of these. To calculate what I like to call the base form of a coterminal angle, simply add or subtract 360 until you are comfortable with the number. So if you say you have 540 degrees and you want to find the angle that is formed on the regular Cartesian plane without extra spins, simply subtract 360 degrees, which turns the coterminal arm backwards. Turns the terminal arm backwards by one full rotation. And then you'll end up with 180 degrees, which is basically just turning this into this. You've subtracted one full rotation from the arm. To demonstrate how to calculate a reference angle, we're just going to do a few examples, and you'll see how it's done from how we approach these problems. It's more intuitive than it is methodical, but if you can draw out the angle, it would become really easy. So let's say we want to calculate the reference angle for a certain angle theta. In this case, I'm just going to draw out my Cartesian graph here. It's 120 degrees. So we see that our degree lands in quadrant 2. But what we're looking for is not theta, but the reference angle for theta. Or, in other words, how far from above the x-axis the terminal arm is. So what we're actually looking for is the blue part. So let's just say theta is 120 degrees. We know that across a line, a horizontal line, there will be 180 degrees. What we can do is we can simply subtract 120 from 180, and that would give us the reference angle, or 60 degrees. This makes sense because here we have a 90-degree angle. We have 30 degrees more than 90 degrees since our theta is 120. And therefore, our theta is 30 degrees past the y-axis. That leaves 60 degrees left, and that means that our reference angle must be 60. Again, these things are generally best visually observed and learned. One can infer how to calculate a reference angle this way, but I'll also put a chart up at the end of the lesson with the formula to calculate the reference angle in each quadrant. For now, let's move on to calculating another reference angle. So let's just say our theta is 210 degrees. So we know that our theta is actually going to end up in the third quadrant this time. So our theta looks something like this, 30 degrees past 180 degrees. There's our terminal arm, and there's our reference angle theta. Notice that the distance between the terminal arm and the x-axis is given by, pretty much is just the extra of after theta is, after you subtract 180 from theta. It's what made it past the 180 degree line. So in this case, our equation would, to calculate theta, would be 210 degrees minus 180 degrees equals theta. And that means we know that theta is 30 degrees. In the fourth quadrant, it would look something like if theta was 330 degrees. So we know that this is going to be 60 degrees past the 120 line. Sorry, not 120, 270 line. So we can just draw our theta like that, and then add another 60 degrees to it. So this is about 60 degrees, and there's our terminal arm. Our reference angle then is just going to be this right here. Now, we know that the reference angle is simply the distance between the x-axis and the terminal arm. Since we've done 330 degrees already, we've only got 30 degrees to go before 360. Therefore, we can subtract 330 from 360. And then we get 30 degrees. That is our theta, or our reference angle. Alright, so now we're on to special triangles. In trigonometry, we have two basic triangles that everybody needs to know. Learning and memorizing these is standard practice, and these triangles can be used to calculate extremely common trig ratios without a calculator. So first off, we have the 30-60-90 triangle. This triangle, like the name implies, has interior angles of 30 degrees, 60 degrees, and 90 degrees. How is this useful? Well, a 30-60-90 triangle will have side lengths of 1, 2, and square root 3, as shown below. These can be scaled up. All you have to do is multiply all three sides by the same ratio, and by similar triangles, the ratios of the sides will still be the same. Basically, you're just turning it from this triangle here into this big triangle. So, you could just write these sides as 1x, 2x, and square root 3x. However, since you're probably going to be using this to find a trig ratio, when you plug all of these sides into the trig ratio, so for example, let's just say we want sine 30, it's going to be equal to opposite over hypotenuse, 1x over 2x. The x's cancel. So if you're just trying to find the trig identities, well, the trig value of the side, it doesn't really matter if you have variables or not, because the ratio is still going to be 1 to 2. A good way to remember this triangle is that the smallest side will always be opposite the smallest angle. So just memorize that this triangle has 1, root 3, and 2, and it has 30, 60, and 90 degrees. Line them up smallest to biggest, and you'll have each side angle pairing. So how can we use this to solve for trig values? Well, let's just say we wanted to solve for sine of 60. Well, why don't we just draw our triangle? We know that one of the degrees is going to be 60. Another one's going to be 90 degrees. So that leaves the third angle to be 30 degrees. And then all we need to do is we need to just fill in our side lengths. 1, 2, and square root 3. Sine of 60 is the opposite over the hypotenuse, which in this case is 3 and 2. So sine 60 will be equal to 3 over 2. Sorry, root 3 over 2. How about, let's try another one. Let's try cos of 30. First, we draw out the triangle, 30 degrees in the bottom, 60 degrees at the top, and 90 degrees as the right angle. Then we plug in the sides. Smallest side, smallest angle. So it's going to be 1, root 3, and 2. Then we take the adjacent over the hypotenuse, because this is equal to adjacent over the hypotenuse. Cos 30 is therefore the adjacent over the hypotenuse. So root 3 over 2. You can try the other trig ratios as well. It works the same way for all of them. Tan is just opposite over adjacent. Yeah. Now the second thing we're going to cover is the 45, 45, 90 triangle. So this triangle is an isosceles triangle. It features 2 equal sides and a 90-degree angle. The side lengths of this triangle will be 1, 1, and square root 2. This is because of Pythagoras' theorem, which states that a squared plus b squared equals c squared. If 1 squared plus 1 squared equals c squared, then that means 1 squared plus c must be equal to the square root of 1 squared plus 1 squared, which is just 2. So there's a little proof there. Just like the other one, this triangle can be scaled up, but if you are asked to find a trig ratio for it, all you need to do is just plug these values right here, 1 and root 2, into the equation. Because the trig ratios only ask you for the ratio of the sides to each other, not their proportion. So let's just say we wanted to find sine of 45. Well, we know that's going to be the opposite over the hypotenuse. The opposite is 1, and the hypotenuse is square root 2. Rationalizing the denominator, we can multiply both sides by square root 2, and then we get square root 2 over 2. Same thing. Cos 45 is equal to the adjacent over the hypotenuse. Notice that the adjacent and the opposite are equal. So this ratio will actually be the same. Again, we rationalize the denominator to make square root 2 over 2. Tan 45, because we have time, is just equal to 1 over 1. Opposite over adjacent. By recalling these triangles, you are basically able to figure out whatever angle that you want, provided that that angle is in one of the special triangles. Now we're going to talk about trig ratios on the Cartesian plane. So this is going to use all of the stuff we've talked about previously, with reference angles, special triangles, coterminal angles, and the different quadrants of the Cartesian plane. What we're going to talk about now is how we can determine both the ratio and the sign of different trigonometric functions on the Cartesian plane. So let's take what we know about triangles, first of all. Generally, in every triangle, we have a length, x, and a height, y. We also have a hypotenuse h, which is given by h squared equals x squared plus y squared. Notice that since h is equal to the square root of x squared plus y squared, and because x is squared, y is squared, therefore x squared must be positive, y squared must be positive. Since x squared is positive, y squared is positive, h must therefore be positive. No matter the sign of x or y, h will be positive. Now let's see what happens when we try to construct triangles in the Cartesian plane based on an angle theta. So we are used to triangles in quadrant 1. But now let's see what happens if we try to construct the same triangle but in quadrant 2. First, let's look at what happens to theta. Since it's the same triangle, we know that the distance between the x-axis and the terminal arm, or in this case, the reference angle, is the same. Visualized, it would look like this. Angle theta is equal. We also know that since they're the same triangle, but they're reflected over the y-axis, the magnitude of the x-axis will be the same, but the direction will be flipped. So in our first triangle, we have base with length x. In our second triangle, it'll also be size x, but it will be negative x instead, because we're flipping the direction and we're going towards the negative direction. So this is going to be negative x as our base size. However, our height, y, remains the same, because both are present above the y-axis, therefore y is greater than 0. Now let's see. Let's try to move the same thing into quadrant 3. Since this time, from quadrant 1, we're reflecting over both the x and y axes, we know that the reference angle is going to be the same, and the magnitudes of x and y will also be equal. However, now the signs of both its base and its height are negative, as x is negative and y is going towards the negative direction as well. Yet, the hypotenuse is still positive. So I'm going to draw that in green. Finally, let's check quadrant 4. We know that x is positive, since the triangle extends rightwards. And yet, y is still negative, because the opposite, or the height, extends downwards. So what can we do with this knowledge? Well, we can use our knowledge of the trig ratios and the characteristics of these ratios in every quadrant to determine what the actual values for different angles in quadrants outside of quadrant 1 are. So I'm just going to do an example with absolutely no values, just to show how the quadrants would change the value of trig ratios. So let's say we had a triangle in quadrant 1 and we had a triangle in quadrant 2. Both of them have reference angle theta, and both of them are of height y and x. However, since the second triangle is in quadrant 2, we must instead draw the base as negative x and the height as still positive y. Now let's just say we were to take the tan of the first triangle. Our tan theta will yield us opposite over adjacent, which is equal to y over x. If we were to take the tan of the second triangle, however, we have tan theta is equal to opposite over adjacent, is equal to y over negative x. Therefore, we can see that as the quadrants of the triangles change, the signs of the corresponding trig ratios will also change accordingly, depending on which quadrant it moves into. So let's say that we wanted to calculate the sine of 150 degrees. We know that sine theta is equal to opposite over hypotenuse. If this were a 30-degree triangle, sine theta would be opposite over hypotenuse, or 1 over 2. Since this angle is outside of quadrant 1, however, we must instead use reference angles to solve it. So if we were to plot 150 degrees our Cartesian plane, it would look something like this. Take your theta, go till 90, and then go over 60 to make 150. There's your new triangle, and there's your reference angle theta, which would be 100 minus 150, that's 30 degrees. As we can see, this puts the terminal arm in a position 30 degrees above the x-axis in the second quadrant. Now let's use the knowledge of the signs of our trig ratios to determine the signs of each identity. So we know that theta is going to be 30 degrees. 30 degrees is opposite 1, with the hypotenuse being 2, and the adjacent being root 3. Since this is asking for the sine of theta, we can simply plug in sine theta is equal to opposite over hypotenuse. Sorry, sine 30 is equal to the opposite over the hypotenuse, which is simply 1 over 2. Notice how, since the x-axis is involved, and yes, I did forget to put the negative, since the x-axis is not involved, our signs remain unchanged as in the third quadrant. Well, let's try another. This time, we want the sine of 210 degrees. Just like last time, we're going to plot out this angle. We're going to take our theta, bring it 180 degrees. Now 30 more degrees. That makes 210 degrees. And then we are going to construct our triangle. Since this is outside of quadrant 1, again, we will use reference angles to solve for theta. Given that we have the middle line being 210 degrees, and the middle line is 180 degrees, 210 is 30 degrees over, which means that our reference angle must be 30 degrees. Now we plot our trig, our perfect triangle. Sorry, I'm stumbling over my words here. We know that the height is going to be -1. We know that the hypotenuse, always positive, is going to be 2. And we know that the adjacent is going to be negative root 3. Solving for sine of 30 in the third quadrant, we get opposite over hypotenuse, which is simply -1 over 2. So the sine of 210 degrees is -1 over 2.